Hey, in this video, I want to go over the answers to the review for the thermochemistry section. All right, the first question is, list 4 ways to increase the rate of a reaction. All right, so basically, like if you've got a chemical reaction going on, what are some things that you could do to make the reaction go a little bit quicker? All right, first thing that you could do is that you could heat it up. All right, or another way you could say that is increasing the temperature. Actually, increasing the temperature would probably be the more technically correct thing. And what that's going to do is going to move particles around faster. All right, it increases the kinetic energy so that it actually does two things. First of all, when things hit each other, they're going to hit each other with a little bit more force. Secondly, there's just going to be more collisions. All right, both of those would tend to speed up a reaction. All right, another thing that you could do is stir or shake it. All right, stirring or shaking something is going to increase the likelihood that fresh reactants are going to hit each other. All right, decreasing particle size. All right, if you have really big chunks, all right, it's going to be hard for the particles in the middle of your chunk to have contact with other things that are in the reaction. All right, so by making things much smaller, your reactants are going to have much more contact with each other. All right, so you can think of the example of sawdust burning really quickly. All right, when you chop up the wood, the oxygen gets in between the sawdust particles, and that allows the combustion reaction to happen a lot faster. All right, the last thing that you can do is you can add a catalyst. All right, and again, what a catalyst does is it reduces the activation energy. All right, we're going to talk a little bit more about that in a later section here. All right, according to kinetic molecular theory, what are 2 things that are required for successful collision? All right, remember the Lego analogy. 2 things that are necessary for the Legos to come together. First of all, they have to be facing the right direction. All right, so you have to have the correct orientation of your reactants. All right, the second thing is that they need to come together with enough kinetic energy. All right, if things, sometimes even if the Legos were oriented the right way, if they didn't come together with enough force, they might just make contact and then bounce off and go their separate way. All right, so you have to have enough kinetic energy. So both of those are required. All right, as I was mentioning before, what a catalyst does is it lowers the activation energy. All right, and so what in activation energy? All right, so this right here is what you call an energy diagram. All right, so this is the total amount of energy that the reactants or the products would have. All right, in this particular example, this is an exothermic reaction. One way to think about this is think of your reactants as being the wood and your products as being the ashes. All right, and if you think about it, which has more possible energy, the wood or the ashes? All right, well, the wood has more possible energy. All right, you could burn it to get some energy out of it. All right, you can't really do anything with the ashes to get energy out of that. All right, but in order to get the wood to turn into the ashes, you have to put some energy into it. All right, so you have to heat that wood up to get the fire started. All right, and that energy that you have to put into a reaction to get it started is what's called the activation energy. All right, notice this right here. This is for an exothermic reaction. What's gonna the thing that you can look at, the way you can look at this and tell it's exothermic is that the products, and I make mention down here, the products, the energy of the products is lower than the energy of the reactants. All right, so wood has a lot of energy, ashes have very little energy. All right, where does all that energy go? All right, when this thing loses energy, that's the heat that's given off by the reaction. All right, so again, with activation energy, if you have a very high activation energy, activation energy is the difference in energy between the reactants and this level right here. It's very hard to get the reaction to go. All right. In fact, that reaction would be very slow because of that reason. All right. So a way that you can speed up a reaction is saying, well, instead of the reactants having to get over this high hurdle in order to become products, make it so that the hurdle's not quite so big. right? And that's what a catalyst does, right? Notice this would be for the same reaction. It's just that this right here, this reaction would contain a catalyst, all right? And notice that the difference between this is, so there's some things that are the same. The energy level of the reactants is the same. The energy level of the products would be the same. The big difference is this is a bigger hump right here than this right here, all right? So when you lower the activation energy, it's a lot easier, it's much more likely that when things collide, they will have enough energy to get over that hump. Therefore, the reaction is going to go faster, all right? So, so this right here would be an exothermic reaction, and remember, an exothermic reaction is a reaction where heat is given off. But there are also reactions that are called endothermic, and that's a reaction where heat is absorbed, all right? Or another way of saying that is that you have to put heat into the reaction for it to go, all right? The big difference is that with an endothermic reaction, your reactants have less energy than your products, all right? So if you think about it, think about just lifting an object, all right? Which has more energy, this object when it's down low or up high, all right? Well, in order to get this object up high, I have to put energy into it in order for that to happen, all right? But then when I put that energy into it to get it up high, it now has more energy than it did when it began, all right? So if for an endothermic reaction, you have to put energy, and usually that's in the form of heat, into it, and that's what allows it to have products that have higher energy, all right? The takeaway thing, though, is just to memorize the overall shape of these, endothermic versus exothermic reaction diagrams. All right. Next question here. Calculate the amount of heat required to amount of heat absorbed when you melt 63 grams of ice at 0 degrees Celsius and converting it into water at 0. All right. So if we're using our diagrams, you should be able to note that that's going to be from this point on the heating curve to this point right here. And these would be the values that you could plug in. All right. 334 is the heat of fusion. All right. And M is the mass. All right. Note that this same equation would be the exact same equation if you were going from water at 0 degrees Celsius to ice at 0 degrees Celsius. The only difference is that's the amount of heat that would have to be released in order for water to freeze. All right, guys, so these would just be opposite processes of each other. Okay. In the next problem, it says how much heat is released when 10 grams of water is cooled from 75 to 25. All right, if you're going to put dots on your heating diagram, it would go from about here to about here. All right, and the equation that governs the amount of heat either gained or released on any of the diagonal lines of this is mCp delta T. All right, where the mass, the specific heat, and the change in temperature. All right, so you would just use these numbers right here. All right. In the next problem, how much heat is absorbed when 47 grams of magnesium is heated from this temperature to this temperature? All right, again, we're not talking about water here. All right, so we're going to need to find the specific heat of magnesium. You can do that just by reading that off of your reference guide. So plugging in these numbers, you would do that. All right. Keep in mind, in these types of problems that involve waters, heating curve, sometimes you have to put some of these together. For example, you might have to go from here to a point here, and in that case, you would have to put this equation in and add it to this part of the equation right here. So remember from those practice problems, there's a lot of different types of questions that can be asked in a situation like that. All right, so using this heating curve right here, let's see, let's make that a little smaller. All right, what are some types of things that you would have going on here? All right, I'm just going to go ahead and let you read these off here. All right, for example, boiling point. All right, that would be D. All right, so if something's boiling, it's going to be going in this direction right here.